which means planar. Okay, so the ones that all the parts move in parallel planes. They don't go out in the vertical direction, right? So let us consider one body, rigid body on the plane. How many degrees of freedom does it have? Body on the plane. We had it already. We had a rod on the plane. It had 3. So how can this one have 2? Right? So you can, for example, describe the position of this point and the angle on some line on that body, right? So this is 3 degrees of freedom, and or in the mechanism slang, mobility equal to 3, right? Now, how about the system containing 2 rigid bodies? How many degrees of freedom? 6, because you need 6 numbers to describe the position of the system, right? You need 3 for the first body and 3 for the other one. Unescapable conclusion, right? Okay? So now we create a mechanism and we start connecting this thing using joints, right? Or kinematic pairs. Okay? So what happens? So our mobility will be equal to 3 times n minus 1. So this will be the number of degrees of freedom or the mobility of our links. N is the number of links. Okay? Why n minus 1? Why not 3n, but 3n minus 1? Because the convention is to assign number 1 to the ground. So link 1 is the ground, and ground doesn't move. Okay? So when we have n links, n minus 1 links will be moving, because link number 1 will be ground. Okay? So this is the number of degrees of freedom of n unconnected or disconnected links, out of which 1 is the ground. Okay? And then we subtract degrees of freedom by putting in joints, right? So let us call by F1 single degree of freedom joints. Okay? So like revolutes or prisms or helical. Okay? Actually in 2D it's only revolutes and prisms. So each of these joints will subtract 2 degrees of freedom, right? So F1 will be the number of single degree of freedom kinematic pairs in the mechanism, and they will subtract 2 degrees of freedom each. Okay? And then perhaps we can imagine some strange F2 joint which has 2 degrees of freedom in the plane. I don't know what it could be, but let's have it. And then they will subtract one degree of freedom each. And suddenly, this is all to it. This is the thing that is called mobility formula. Okay? I have the same stuff here, but a little bit better handwriting. Okay? So this is the equation for mobility in 2D, which is found in books, and it is called mobility formula or mobility equation, or sometimes Kutzbach criterion, or sometimes Grubler's formula. Okay? Different books, different. Probably many originators of this idea independently, right? Somewhere in the mid-19th century. So this actually fulfills the idea of a threshold concept, because without knowing this equation, you were totally stuck on the initial question when you had a 6-bar mechanism, right? But with this equation, we can immediately go back to this and do the calculation, right? So let's do it. Now, a word of warning. The mobility equation requires the user to turn off his brain or her brain. No thinking involved. Just count the number of links, number of joints, substitute. As soon as one begins to think, it stops working. Okay? So this is the thing that requires the user to refrain from thinking. So we have, for this one, m equals to 3 times, how many links? 1 for the ground, 2, 3, 4, 5, 6. 6 minus 1. Take away how many F1 type joints, single degree of freedom joints? 1, 2, 3, 4, 5, 6. 6 times 2. And here nothing. Okay? Which is 15 minus 12, which is 3. Okay?